Hi everybody, Mary here. And this week is all about heat. Matter of fact, it's this week and next week. This is a big chapter. It is going to be in our OpenStax textbook. It's actually going to be chapters 13, 14, and 15. And I call it chapter 14 because one, it's in the middle. And we do a little of 13 and all of 14 pretty much and a little of 15. So it kind of works in my little crazy brain. We're going to start out talking about linear expansion, the fact that when things get hot, they expand, and volumetric expansion. When things get hot, they expand volumetrically as well as just linearly. Then we're going to go into heat transfer. How much heat is transferred from one object to another, and it depends on the type of object you have. Some things are really good at transferring heat, like metal. That's why you use a cooking pot. Metals are really good at transferring heat. Things that are insulators don't transfer heat really well. So we're going to do the math for that and talk about what makes an insulator, what makes a conductor of heat, and things like that. We're going to get into latent heat. Latent heat is hidden heat. Heat that is hidden by the state of an object, whether it is in a solid, a liquid, or a gas. We're going to talk about calorimetry. How do you measure calories of heat within a substance when those heat calories get transferred? And we're going to use energy units, joules, calories, in situations with heat as opposed to just energy, because heat is a form of energy. We're going to get into forms of heat transfer, conduction, convection, radiation, how all of those work, and a couple of those have formulas that go with them. We're also going to talk about the laws of thermodynamics, and these are the big basic rules of how heat works. These are as basic to heat as Newton's laws are to dynamics. So big ideas. It's going to be 2 full weeks, and you're going to have 2 labs to go with this heat chapter. So let's take a look at Canvas and let's take a look at what we've got coming up. There will, of course, be a study guide and homework problems, and the study guide and homework problems will be due at the end of the 2-week time period. Homework problems, there's 26, so please work a little of those at a time. If you work till the raggedy edge of the end, you're going to be stressed out. Each one of the topics, of course, has a page. The first lab is due at the end of the first week, and it's the only lab that is due, the only thing that's due at the end of the first week in our 2-week heat fandango. And remember, the dates in the videos, those are going to change from semester to semester, so please look in your Canvas course for the correct dates. The end of the second week are going to be the study guide, the homework problems, the second lab, Latent Heat Lab, plus the concept quiz and the problems test, and it will cover all of heat, plus the module we did prior, which is the pressure module. So a nice big test. Pressure was small, only had a couple little equations, but that will be part of the test that's coming up. So let's spend a little time talking about these 2 labs, and we'll talk specifically, let's begin with the first lab of the 2, which is the specific heat lab. Now, this whole lab is about heat transfers between materials, and we're going to look at conservation of energy. You are going to use from your lab-in-a-box materials, you're going to use the calorimeter cups. Okay, I know it's 2 styrofoam cups and a little plastic coffee lid, but it works actually very, very well. So one styrofoam cup is pretty good at preventing heat loss. You put one inside of the other and hey, it's really good at preventing heat loss. So you're going to pour everything inside of this cup, and then the extra one is there as just extra insulation. The lid helps prevent heat loss once you have the mixtures created. For the very first lab, you're going to need some cold water. So throw a beaker full of water into the refrigerator right away, and then you're going to get everything else started. The primary equation you're going to use for this lab is Q is mc delta T, and there'll be some lectures on that in the lecture portion of the course. first part of the lab, and there are 3 parts, you're going to make 3 mixtures, is going to be mixing a lot of cold water and a little bit of hot water. So here's the basic setup. 50 milliliters of cold water plus 10 milliliters of hot water. I heated the hot water in my microwave with a measuring cup. You could certainly do this in a microwave safe mug. The cold water I put in a beaker. I use cold tap water, and then I put it in my fridge to get it extra cold. You're going to measure each of those in the graduated cylinder and pour them in the extra cup, see, labeled extra cup. Take the temperature in here, and then you're going to mix them in the calorimeter. Once you pour both of these things together, you're going to take the temperature of the mixture every 15 seconds, and the highest temperature it reaches during this period of time will be considered your final temperature. You're going to need to know the mass of things as you go along, and you're going to find the mass of just the cold water, mass of just the hot water by subtraction, massing by difference. We do this all the time if you've ever taken chemistry class, and so just do some subtraction and that should be pretty easy. Then you are going to do the basic equation. The basic calculation here is the heat that is lost by the hot water is going to be equal to the heat gained by the cold water. That's the basic setup, and when you've gotten to this point, you should have watched enough videos and lectures that should not be hard for you to set up. Please keep in mind you do not need to include the cup in the calculations. That's why we're choosing styrofoam. We're choosing styrofoam because we're going to make the assumption no heat get transferred to that cup. So you're going to measure the final temperature, calculate that final temperature, and do a percent difference between the two. Use the same equation that we use for percent error. And as always, show me everything with units. Part 2, you're basically doing the same thing with different amounts of water. 50 milliliters of cold water and 50 milliliters of warm water. Same thing, mixture, measure the temp upon mixing, show me the calculations, and then the percent difference between the two. Part 3 gets different. You're going to heat some pieces of metal, and how are you going to heat them? You're going to tie a string around 5 metal washers. You're going to need their mass ahead of time prior to adding the string to them. How you're going to heat them is tie a string to them, leave a long tail on that string, tie that string, attach it to some sort of a long wooden spoon or a spatula that is wider than your cooking pot. Fill a cook pot full of water, put that to boil on a stove, and then you're going to suspend the metal washers inside that water. You want the washers underwater but not touching the bottom. That combination is what is going to give you the original temperature of the washers. When you take the temperature of the water, don't let the thermometer rest on the bottom of the pot. You want to hold this in the water, not resting on the bottom, and the original temperature of the hot water will be equivalent to the original temperature of that hot metal. You're going to put that hot metal into your calorimeter cup with some water. I transferred it, spoon and all, string and all. The little difference in the string is not a big deal. This will reach an equilibrium temperature. A difference here is you're going to time this every 15 seconds for 2 minutes. Why a little bit extra time? It takes a little extra time for that heat to come out of that metal and go into the water. You're going to record the highest temperature here as the final temperature of the mixture. Again, calculate the specific heat, this time of the metal washers, look up the true value, find me a percent error. So this is a longer lab because you're doing 3 mixtures, but this is the lab due for the first week of our heat chapter. The second one, the second lab, is the latent heat lab. Now, latent heat is heat that is stored inside of the state of an object due to it being a solid, a liquid, or a gas, or the amount of heat needed to break the bonds to make it go from a solid to a liquid to a gas. This graph is important when we talk about latent heat, and there's going to be a whole lecture on this, so I'm not going to go into it right now. This chart, I'm going to ask you to fill this in to bring these ideas forward in your brain. What you're going to do in the latent heat lab is you are going to take a piece of ice and you are going to put the ice into the calorimeter cup and ask some warmish water plus a piece of ice, and ask those to reach thermal equilibrium. Now, the size of the ice cube is a big deal. You do not want a tiny little shard of ice. You also do not want a big honkin' ice cube. I have an ice maker, and if you have an ice maker, one standard ice maker ice cube is kind of perfect. If you have a standard ice cube tray, make like half-size cubes and you're going to be in good shape. So if you don't have ice in your home right now, start making smallish ice cubes, not tiny, but like half-size ice cubes, and you'll be perfect. One of these will give you good results. I just did this lab when I wrote it up, and I got 6% error. And if I can get 6% error, you can certainly get good results. You're going to need to take the original temperature of the ice, which is going to be pretty much the original temperature. I shoved my thermometer into my ice maker ice box area, and that worked really well. If you are making your ice cubes by setting your ice cube tray in your freezer, take the original temperature of that freezer, but let it sit there a while, make sure it works. And don't set this thermometer right on the bottom of your freezer, because it might test not the air, but the actual freezer elements, and that'll give you too cold a temperature. Again, you're going to mass things by difference, and the calculation here is going to be one big honkin' calculation. Again, heat lost by one thing is going to equal heat gained by another, and I asked you some questions to help get your brain in the right spot. One big calculation here. By this point in the chapter, you should be able to do this. And then lastly, here are some true and false questions to see if you understand this latent heat stuff. So that should do it, ladies and gentlemen. As always, if you've got questions along the way, shoot me some emails, and enjoy heat. It's a fun chapter. I think it's very relevant because you pay for heat. You worry about your heat bills, and you worry about staying warm and staying cool in the summer. So heat's a big deal. All right, we will talk to you soon, and have a grand couple of weeks. Bye.